Space-time diagrams part 3, and now we get to bring in the special theory of relativity. So we've got one of our standard situations here. Let's revisit it. We'll have Bob traveling in a spaceship, and in the positive x direction to the right at velocity v, Alice will be observing. And if we wanted to plot Bob's world line in Alice's frame of reference, it looks something like this, of course, depending on what the actual velocity was, but the slope here is simply going to be 1 over the velocity, as we've talked about and reminded ourselves in a previous video clip here. These dots here are not important. I was just sort of trying to get a nice plot there. So we can see, actually, if we wanted to calculate the velocity here, and we're assuming from now on that our units are going to be, say, in light years for x and years for time, or perhaps light seconds for x and seconds for time. But that gives us c, of course, speed of light being 1 light year per year, or 1 light second per second. So again, if we were to plot a light beam going out from the origin, it'd be at a 45-degree angle, slope of 1 here. And we can see Bob, at least on our plot here, is traveling such that looks like in 2 years, say, he goes 1 light year, right? And in about 4 years, he goes 2 light years. So it looks like he's going at about 0.5, 1/2 the speed of light there. So this, the slope would be, actually the slope is 2 here, and therefore velocity is 1/2, in other words, 1/2 the speed of light. And so that would be Bob's world line in Alice's frame of reference, straight line, because he's going at constant velocity there. If we were looking at it from Bob's perspective, from his frame of reference, of course, he's sitting in his cockpit. As far as he's concerned, he's at rest, in his lattice of clocks and so on and so forth. And he sees Alice receding behind him. So it looks something like this to him if he was to plot Alice's world line in Bob's frame of reference. He would see Alice receding backwards. So the slope here, if we were to put that in, slope equals -1 over v. It's sloping downward. And so essentially Alice is going at -0.5 the speed of light to the left as far as Bob is concerned. And so we can see there's symmetrical situations there. That's how Bob sees Alice in his frame of reference. That's how Alice sees Bob in her frame of reference. Now for any given point, though, remember, we have the Lorentz transformations. So given, say, in Bob's situation, a given space-time point, like this one right here at -2, 4, if I wanted to find the corresponding point in Alice's frame of reference over here, it would not be -2, 4. Okay? So this point here, -2, 4, I'd plug it into the Lorentz transformation. That would go from Bob's frame of reference to Alice's frame of reference. So this is sort of our standard one here. We could plug in the coordinates for Bob, that point he measures in his space-time point in his frame of reference, and we could find the corresponding coordinates in Alice's frame of reference. So obviously we need v, so we could calculate gamma and do the calculations and get the actual results there. Or if we had a point in Alice's frame of reference, she sees a flash of light, an event, or something happens at a certain x and t value in her frame of reference, we could figure out the coordinates that Bob would see it in his frame of reference using our second set of transformations. And remember the minus sign here. So our standard situation, our standard set that perhaps we memorize, is this one where we have the frame of reference, in this case Bob moving to the right, Alice observing. And then if we have the opposite situation where something is moving to the left, we just change the minus sign and be careful that we have everything set up correctly there. So that's nice. What we'd like to do is somehow, could we put Bob's plot on the same plot as Alice's plot? And because it's just not a one-to-one correspondence, you can't just take this and put it over here. The Lorentz transformations tell us it's going to be a little bit more complicated than that in terms of going from a certain point in Bob's plot to a certain point in Alice's plot. In the previous video clip, we had those skewed plots, as it were, those non-square plots, to show you how it might work. And this is going to be very similar to that. We're going to do it semi-quantitatively. We're not going to go into all the details to do it precisely, but we want to get the basic idea here, because as we'll find, it's going to be useful later on, which is why we're doing it, of course. So let's start off and just say, okay, here's the T sub B axis in Bob's frame of reference, right? And actually, remember, that would be the line of same location. That is xb equals 0. So that's actually Bob's location in his frame of reference. The x, if we were to draw his world line on here, Bob's world line, it would just look like this. Go right along the x-axis there, the x sub b axis, because that's where he's located in his frame of reference. He never moves from that position. Same thing for Alice in her frame of reference. Her position would be, her world line would be, right along the x sub a. The T sub a axis at xa equals 0. Okay. So our question here is then, if we want to draw the T sub B axis in the context of Alice's plot here, what do we have to do? Well, essentially, we just have to plot Bob's location. The TB axis in his frame of reference is his location. Well, we've actually already done that. This is Bob's location at any given time in Alice's frame of reference. So actually, we can even just say something like this. We'll erase the Bob there. Put a little arrow on here. This is the TB axis. Bob's T sub B axis in Alice's frame of reference. That's his line of same location. In Alice's frame of reference, his line of same location is that. That's the line, the world line he's on. Here, it's just a straight vertical line. Okay, so we see it skewed a little bit. Maybe you can see now the similarity to what we were doing in the previous video clip. Could we actually, that's sort of qualitatively, could we do it quantitatively as well? And yes, if we look at the Lorentz transformation here, and we say we want TB equals 0. Okay, so we're going to say we want TB equals 0. I'm sorry, no, not TB equals 0. We want the TB axis is XB equals 0. That's Bob's location. Okay, so we're concentrating on the TB axis here. XB equals 0. Let's look at our equations here. And a particularly nice one is this one right here. Okay, let's just write that down over here. In fact, XB equals gamma XA minus VTA. I've got XB equals 0. The Lorentz transformation says that's equal to gamma times XA minus VTA. That's a true equation. And if XB equals 0, then we can see this thing equals 0. And that also means that, just to be clear about, let's just put an equal sign over here. This means gamma XA minus gamma VTA equals 0. Just multiply through by gamma there. And then bring this to the other side. So what that means is gamma XA equals gamma VTA. And those of you who've done a fair amount of algebra recently, you can jump ahead and see this in your head already. But what's our result then from this? Well, the gammas cancel. We have a gamma on each side, so we can get rid of those. And we're just left with XA equals V TA, or another way we can write that is TA equals 1 over V X sub A. Just divide each side by V and sort of switch the order there. Okay. The reason I wrote it in this form here is because this is our standard form for writing. You may recognize that as an equation of a line. Way back when we did a little math review on that. We're not going to push this too hard here. But quantitatively, for those who are familiar with this, essentially the T value here is my vertical axis. The X values are the horizontal axis. And the 1 over V here is the slope of any line that I've drawn here. So this is telling me that when XB equals 0 for Bob, which is his TB axis, the equivalent line on Alice's frame of reference is of this form. T sub A equals 1 over V X sub A. And that is exactly this line here with slope 1 over V. It goes through the origin. For those of you who remember about the y-intercept of the equation of the line, the y-intercept is 0 here. Again, we're not going to push that too hard. For those of you, it's or very fuzzy on it. I can't remember what we're talking about there. The point being here is that by setting xb equal to 0, that is the TB axis in Bob's frame of reference, and using Lorentz transformation, we can find the coordinates of the TB axis, an equation really for those coordinates for the world line in Alice's frame of reference. It turns out to be a line like this with slope 1 over v for whatever the velocity of transformation is there between the two frames of reference. Okay, so we've drawn part of Bob's frame of reference now in Alice's frame of reference. You also might say, before we go on to the x-axis here, what about, this xb equals 0 is a line of same location. What about other lines of same location? Okay, so over here, lines of same location are good in green here. That's the same location. That's xb equals 1, 2, 3, and so on and so forth, or 1.5, whatever you want to do. Could we transform these lines of same location and also put them on this plot here? In other words, we're starting to take Bob's grid, the vertical lines here at least, and reproduce them on Alice's plot. Well, to do that, just to indicate that, this line is, that's 1 right there, xb equals 1, we'd say xb equals 1, and by the Lorentz transformation, that equals this equation, gamma xa minus v t sub a, and just a little bit of similar algebra here. We could get an equation out of this, somewhat similar to this, although this time we'd have a y-intercept value in there. And what we'd find is we get a line something like this. Let's get rid of the slope part here now. We've seen that. So we get, not quite like that. Let's get a little straighter than that. Try to get it in here. Something like that. In other words, it would be parallel to the TB axis. Just like the lines of same location here are parallel to the TB axis, when we transform it to Alice's plot, the lines of same location will be parallel to the TB axis. So they'd be diagonal lines like that, parallel to this TB line we have here. This is how you could do it actually quantitatively, mathematically there. Okay, so the vertical lines over here in Bob's frame of reference, his grid, the space-time grid, transform into lines at an angle, slope 1 over v, actually, and then the lines of same location for each of these would transform into parallel lines over here. Okay, so that's part of the grid. That sort of takes the lines of same location in Bob's frame of reference and transforms them into lines of same location in Alice's frame of reference. Now note that Bob's lines of same location are at an angle here. Alice's lines of same location, of course, are still vertical lines here, so they're different. A line of same location for Bob is not a line of same location for Alice. Okay, now let's look at, so we did this. Let's look at now the xb axis. We like to take the xb axis here, and what does it look like if we put it on Alice's plot? So, xb axis. So we want the xb axis here. And the xb axis, of course, is when tb equals 0. Times t sub b equals 0 here. Okay, so t sub b equals 0. And if we look at our equations over here, we can use different ones, but this one in particular is a nice one to use because we've got the TB all by itself here. It's going to equal 0, so we can say this equals gamma times TA minus v over c squared xa. Okay, and again we'll just say that equals 0 because for this special case, for the TB equals 0, the x sub b axis, well, we can solve this equation for xa in terms of TA. In fact, we won't multiply it out this time because we should be able to see that if I've got something times something equals 0, that means either this is 0 or this something is 0. Clearly, gamma is not 0. It's greater than or equal to 1. That means this must be equal to 0. So this implies that TA minus v over c squared x sub a equals 0. And from that, we get t sub a equals v over c squared x sub a. And that is our result for it. And again, if you look at that, you say, in Alice's frame of reference, with t being the vertical axis, x sub a being horizontal, this is the equation of a line with slope v over c squared. Okay? And no y-intercept, actually. So what that would look like if you actually put in some numbers here and plotted it, we'll just give you the result here, is it looks something like this. Let me see if I can get this more or less. Well, it's something like that. That would be the x sub b axis, because remember, so x sub b axis is when t b equals 0. So we plugged in t sub b equals 0 using one of our Lorentz transformation equations and got an equation that is true when t sub b equals 0. Okay, that's important. This equation is not true just in general. It's true for the case t sub b equals 0. So Bob's horizontal axis here, the xb axis, transforms into Alice's plot as a line with that slope, as you can, in fact, slope v over c squared. And we could do lines of simultaneity as well. Again, the lines of simultaneity here would be t sub b equals 0, t sub b equals 1, t sub b equals 2, or really any t sub b. T sub b equals 3.896, as a line of simultaneity. And again, to do that, same idea here. We just say t sub b equals 1. Okay, that's a line of simultaneity here. This line of simultaneity for Bob equals, again, our equation gamma ta minus v over c squared x sub a. And we could solve that again, put it in a form somewhat like that. And we'd find that the lines of simultaneity for the xb axis here on Alice's frame of reference would be parallel to the x sub b axis. So they look something like this. And the lines of same location, look something like that. And now that should look familiar to you, especially. This was our case we did in the previous video clip, where we did over here on this side, where we had the very skewed axes, both of them at angles that were not vertical or horizontal. And that's why we did it, to show that now we have both Bob's frame of reference and Alice's frame of reference, or really their space-time diagrams, on the same plot here. And so note that any given point, let's do a red point here. Okay, let's just put, let's do a relatively easy one here. So we'll do it about right here. Okay? Now, imagine if we went back to the surveying example and we were doing a plot of land. That red dot would indicate a certain position at that plot of land. And that's constant. It's invariant. It's just that, say, the location of the well on the plot. On a space-time diagram, that red dot represents an event, say a flash of light. You could take a photograph at that position and verify, yes, that's where it is. But as we've seen, Bob and Alice would have different measuring systems for saying exactly what location and what time that occurred. And we can get that now off of these plots. So this event here, one reason I chose it, because it's very easy. In Alice's frame of reference, she said, I saw that flash of light, took a photograph of it, and it was at x equals 3, t equals 4. Okay, so at time t equals 4, maybe 4 years, and 3 light years away from my origin, that flash of light occurred. And then the question is, where does Bob measure that flash of light in his coordinate system? Well, it's a little trickier than we can do on this diagram. We'll talk about that a little bit more in the next video clip. But clearly it's not at 3, 4. 3 over and 4 up. For Bob, maybe it's at something like this is like 1, 2, and then 1, 2, maybe 3. So roughly 2, 3 in his diagram. Now that's very qualitative. It's not going to be exactly like that. But hopefully you see the idea here that by putting both coordinate systems really on the same plot, first of all, we have to skew Bob's axes here to get to work. But we can still see his lines of simultaneity. They're not going to be just vertical and horizontal. They're going to be parallel to the xb axis. for the lines of simultaneity, and parallel to the TB axis for the lines of same location. So to Bob, anything that happens along this line here is simultaneous to Bob, or that line. Anything that happens on one of these lines are things that happen at the same location throughout time. And so Bob himself in his cockpit is sitting on this line, or really moving along that world line as he moves through time here. Okay, so we're going to exploit this a little bit later on, especially when we look at things like the twin paradox and the pole in the barn paradox, and we'll also do some more examples of this as we go along.